Welcome back to thermochemistry and thermodynamics. In part 4 of this unit, we're going to be calculating delta H a fourth way, that is using calorimetry, and on the way to do that, we're going to be looking at heat capacity and heating curves. Let's go. So calorimetry is the measurement of heat transfer. Heat flow cannot be measured directly, but temperature can be measured before and after a reaction, and then that data can be used to determine heat transfer. So heat transfer, that's the Q. That's the heat gained or lost, as you hopefully remember from part 1. Then we have M. M stands for mass. That's the mass of the thing that we're looking at. C is the specific heat capacity of a substance. That's the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. The specific heat capacity has to do with how much energy it takes to heat or cool something. And then delta T is the change in, well, that's supposed to be in temperature. That's the change in temperature. You may also see the formula Q is equal to mHF, where HF is the heat of fusion, how much energy it takes to melt or freeze something. And you may also see it written as Q is equal to M times HV. HV is the heat of vaporization, how much energy it takes to boil or vaporize. So MC delta T is heat cool. MHF is melt freeze. And then MHV is boil condense. In order to do that, we're going to need a heating curve. Hopefully this looks familiar from Chemistry 1. So this heating curve has, at the lowest temperature, you've got something in a solid phase. As that solid he starts to heat up. When it gets here, then it's going to start to melt, so that's your melting point. As it's melting, it's a solid and a liquid together. Once it finishes melting, notice that it's melting at a constant temperature. For water, that's 0 degrees. Once it's finished melting, now it's a liquid, and now it's going to heat up. At a certain point, it gets to its boiling point, and for water, that point is 100 degrees. Notice that the temperature is constant while it's boiling and changing from a liquid to a gas. Let's make that prettier. And then once it's heated all the way, that liquid has completely boiled, now it's a gas. If we go back down, starting as a gas, it's going to start cooling to a liquid, and then it's a liquid that cools, and it's going to get to its freezing point. So we're going to label these things on the graph. Heat of fusion is energy required to melt freeze. That's right here on this bottom flat line. This is 335 joules per gram. Then we have to heat cool. That's the specific heat. So I'll put SPHT in really bad handwriting there. That's 4.18 joules per gram degree C. And then once it's boiling, then it's vaporizing. That'll be along the liquid gas line. HV is 2260 joules per gram. Again, this whole chart should look really familiar from Chem 1. So let's start just working these example problems. How much energy is required to raise the temperature? So this is going to be heat cool of 10 grams of water from 20 degrees to 50 degrees. So if you're thinking about this heating curve chart, on this heating curve chart, we're going to be in this section because we're heating, cooling, specifically heating. So the formula, Q is equal to MC delta T. The M, the mass, is 10 grams. The C, the specific heat for water, this part of the graph, is 4.18 joules per gram degree C. And then the delta T is the change in temperature from 20 to 50. That's 30 degrees change. You don't have to use Kelvin here because we're looking at changes in temperature, not absolute temperature. So if you added 273 to both of those numbers and then subtracted from each other, you would still get 30 as your change. So Celsius is fine to use here in this type of problem. So you'd use multiply. 10 times 4.18 times 30 degrees is 1254 joules. The grams canceled, the Celsius canceled, joules was left. And that's it. Let's look at another. Draw the heating curve. How much energy is needed to raise the temperature of 10 grams of ice from 0 degrees? We're going to have to melt the ice. Then heat it up to 80 degrees. We're going to be on two parts of this line. So this will require two separate formulas, two separate energy calculations. How much energy does it take to melt the ice? Then, how much energy does it take to heat the water once it's melted? Two sets of things. So for the melt the ice, this is not MC delta T. This is Q is equal to MHF. The M, the mass, is the same, 10 grams. But now we're looking at HF, not specific heat, and that's 335 joules per gram. So multiply that, you get 3350 joules just to melt the ice. Once it's melted, and now it's liquid water at 0 degrees, my new formula, Q is equal to MC delta T. M is 10 grams still. C now is this part of the line, so that's 4.18 joules per gram degree C. And then the change in temperature from 0 up to 80 is an 80 degree temperature change. So 10 times 4.18 times 80 is 3340 joules. So pretty much what that's telling us is it took 3350 to melt it, and then 3340, sorry, that's 3344. Hopefully your calculator caught that and you were waiting for me to catch that. 3344 to heat it. So to find out how much it takes to melt and heat, just add those together. 3350 plus 3344 is 6694 joules. It's not always going to be water, because water is not the only thing that you want to heat or cool or melt or freeze. Sometimes it's going to be something funny like aluminum. So you cannot use the 335 or the 2260 or the 4.18. You're going to have to use a different number. But it's the same process. We're looking at the heat cool. So we're looking at the formula Q equals MC delta T. So M, that's 21 grams. Delta T, that's 260 minus 25 is 235. The only thing that's weird here is the C. You're going to have to find your own specific heat for aluminum. So go back to your reference chart. In your reference chart, there's the delta H, S, and G first couple of pages. The last page has to do with information about every element we know. There's all sorts of really good stuff. It's in alphabetical order, so you'll find aluminum. It's the second one down. Then follow aluminum over all the way over to the column marked specific heat, and that is 0.900. The decimal's kind of hard to see there. 0.900, and the unit is joules per gram degrees C. So then all we got to do is multiply. 21 times 0.9 times 235 is 4441.5 joules. And that's your first blank, and we're good. But the problem is, it also asks for delta H. So we're also going to have to do delta H. Now, delta H is typically given in kilojoules per mole. The units for delta H are kilojoules per mole. That's a problem here because we have joules instead of kilojoules. I'm going to change that first. 4441.5 joules. 1,000 joules per kilojoule gives me 4.44 kilojoules. Now that's how many kilojoules per 21 grams of aluminum, but not how many kilojoules per mole of aluminum. So now I'm going to take that 21 grams of aluminum and convert it to moles. So 21 divided by 27 is 0.778, let's say, moles. So delta H, being kilojoules per mole, well, we have 4.4415 kilojoules and 0.778 moles. All we got to do is divide that, and I get something close to 5.71 kilojoules per mole is the delta H for that reaction being heating or cooling aluminum. Let's do another one. 100 joules of heat are absorbed by 55.85 grams of iron, and the resulting temperature change was 3.98 degrees. Calculate the specific heat of iron. Do not look it up on your handy-dandy reference chart. We're going to calculate it and then compare it to your handy-dandy reference chart. So, we're talking about temperature changing, heating and cooling, not melting or freezing or boiling iron. So my formula is Q equals mc delta T. This 100 joules is the heat absorbed. That is Q. So it's going to be 100 joules equals 55.85 grams of iron times the specific heat of iron. Do not look it up. This is what we're solving for. Times the change in temperature. Temperature change was 3.98 degrees Celsius. Solve for x. Let's see, we're going to divide both sides by 55.85 grams and 3.98 degrees C. Divide both sides by. And that way we'll cancel out these guys, and we end up with x is equal to 0.45 joules per gram degrees C. Okay, now you can look it up. It's like 4498. That's really close. That's a pretty good experiment. Let's do another example. We're going to calculate the specific heat of lead using the following information. 106 grams of lead at 100 degrees are placed into 100 grams of water at 23 degrees. The final temperature of the system is 25.5. So I took hot lead and put it into relatively cold water, and so the lead heated up the water got heat by the lead. So we're looking at heat lost and heat gained. What we know is Q is equal to mc delta T. And Q can represent the heat lost or the heat gained. But since this is an isolated system, or at least for the sake of argument, we're going to assume it's an isolated system, the lead is losing heat to the water is taking heat from the lead, the amount of heat lost by the lead is the same as the amount of heat gained by the water. So the M of the lead times the C of the lead times the delta T of the lead, essentially energy lost by lead, is equal to the M of the water times the C of the water times the delta T of the water, or energy gained by the water. Essentially, we have mc delta T equals mc delta T. So now let's just solve. So the M of the lead, that's 106 grams of lead. The C of the lead, that is what we're solving for. Put an X there. The delta T of the lead, well, it was 100 degrees, and then when it finally finished reacting, it ended up at 25.5. So if we subtract that, we end up with 74.5. That's my delta T for the lead. The water, that was only 100 grams instead of 106. The specific heat of water we know is 4.18. Let me write that nicer. And the change in temperature of the water, well, it had 25.5 at the end, but it started at 23. So if we subtract those, we get 2.5. The water changed by 2.5 degrees. So solve for x, which means dividing both sides by 106 and 74.5, so that we cancel out what we don't need. And we end up with x is equal to 0.132 joules per gram degrees C. Check with the reference chart. Hopefully that's pretty close. All right, last example. What's the final temperature of a system prepared by placing 210 grams of iron at 100 degrees into 100 grams of water at 23 degrees? So the iron's going to cool down and lose heat to the water. The water's going to heat up because it's gaining heat from the iron. So what we're going to have is M of the iron, C of the iron, delta T of the iron is equal to M, water, C, water, delta T, water, because the heat lost by the iron is equal to the heat gained by the water. So now all we're looking for is the delta T, essentially the final temperature. So let's plug in everything else. The mass of the iron is 210 grams. Specific heat of iron, since that's not what we're looking for here, you can totally look it up on your chart, 0.448 joules per gram degrees C, or you can use 0.45 like we found in example 16, times delta T. I'm going to leave that blank for the moment. The mass of the water is 100 grams. Specific heat of water is 4.18 joules per gram degrees C. And delta T, I'm going to leave that blank for just a moment. Let's think about what delta T is. That's the change in temperature. So when we had our previous problem, when we were looking for the specific heat of lead, that was 100 degrees lead went down to 25.5. And then it was 25.5 as the final temperature, started at 23 for the water. So we're solving here for the final temperature. When the final temperature is lower than the initial, we're going to take the initial temperature minus the final. When the final temperature is higher than the initial, we're going to take the final temperature minus the initial. So down here in this problem, this is going to be my original 100 degrees minus x. And this will be my x minus my original 23 degrees. So kind of look back at the example problem from before to see why, if that's still confusing you. Okay, now all we have to do is solve for x. So the first thing I'm going to do is multiply 210, 210 times 0.448 times 100, and then 210 times 0.448 times negative x. And I end up with 9408 minus 94.08 x. On the other side, it'll be 100 times 4.18 times x, and then 100 times 4.18 times negative 23. So I have 418x minus 9614. Then if we can combine like terms, add 96.9614 to both sides, add 94.08x to both sides, you'll end up with 19022 equals 512.08x. Please check my math. Make sure that what I'm doing matches what you're doing and you get where my numbers come from and that you make sure my numbers aren't totally off base. Now we're going to divide both sides by 512.08 and I hopefully end up with x is equal to 37.15 degrees C as a final temperature. And hopefully you got that as well. Okay, well that's calorimetry and the heating curves and everything you need to know about calculating delta X. When we meet again, we'll be talking about entropy and free energy. See you then.